This will be the third talk in a row now on educating people on Zephyr. I think the difference to the two talks before is that we've been focusing on professionals in the field, like education post-university, so to speak. And this is joint work between Stefan Linz and myself. We are coming from different companies, but Stefan and I, we know each other for ages now. And we've been working together and collaborating ever since we moved to different companies, although we once met in a single company. What I like to talk about today is how we can make Zephyr more accessible to professionals in the field. And probably we have heard a lot of this before now, that we're all facing similar challenges, be it in a university course or be it with professionals. First and foremost, embedded computing is just notoriously difficult because it is much more, at least when you compare it to like web programming or JavaScript programming in a browser, you need a lot more tools installed locally. There is only so much that you can infer from the system, whether it has been flashed correctly or there are some LEDs and maybe a serial console, but not a browser window, so to say. And for most of the tasks that you do in embedded computing, you need a basic understanding of hardware. Obviously, it's embedded computing. What we also see is that different backgrounds mean different challenges for the students to approach it. Like, it really depends on your starting point when you enter this maze of embedded computing, because you're struggling with different things. If you're a student without any prior experiences, you're a blank page, and you can learn a lot of stuff much more quickly than if you've been working in the field for 20 years. And then if you're a software developer without any embedded skills, all this hardware stuff feels different and feels strange. And if you're a hardware developer, then you might lack software engineering skills, and you might have never git cloned a repository before, because the hardware and the little microcontroller programs that you were used or that you were asked to develop in the past didn't require these tools. And that's really where the people are coming from, which join us in our meetup sessions. So there might be students, there might be software developers, and there might be hardware developers. And even if you would assume some prior knowledge and some prior exposition to embedded computing, the learning journeys are still different, depending on where you're coming from. Obviously, we see a lot, mostly younger folks, students that have some background, have some time playing around with Arduino. You mentioned Platform I/O, CircuitPython, MicroPython. And I also genuinely believe that this is a great starting point because it abstracts away a lot of the difficulties. It's easy to use, it's easy to get started. But then what we also see, in particular with companies and with startups, most likely with startups, they miss the point where they should have changed technology. And then they're trying to push this Arduino stuff all the way into production. They try to wrap it up in a box and call it a product. This is typically when we as consultants come in and say, no, that's not a product, that's a prototype at best. And then we need to educate them that they probably need to rewrite large portions of their code base. Then there is another big group of people, that's the professionals in companies, which have been used to vendor-specific IDEs and vendor-specific tools. So typically in the past, and that is really only going to change with Zephyr in a sense, you started, the very first choice you made in the system architecture was the microcontroller, and you picked a particular brand, like a silicon vendor, and then from this decision onwards, you were using that specific tool set, and then this was all built around that single microcontroller. And then it didn't really matter whether this was whether you were using a different RTOS or bare metal. You were embedded in this very specific IDE, and this is important because this is where now these professionals, 10 years later, where their expectations come from. Because that was easy to use, it was a graphical user interface, there was one button to press, and everything would work automatically, like one-click installers, which were hiding the complexity of the actual stuff going on completely. And then the third group of people we see, because obviously Zephyr is a Linux Foundation project, is lots of folks from Linux get attracted to it. But they have probably never really worked at low microcontroller stuff. They were used to an operating system, they were used to huge amounts of memory and so forth. And they were also used, and this is the interesting point here, to command line tools. So they are probably the easiest to get onto the tooling side of Zephyr, but then the embedded part is where they struggle with. So we need to find something that more or less works for all of them. At least that was the challenge that we are facing. And this is the problem here with Zephyr, if you follow this, because it just means that Zephyr has some misalignment with these needs and expectations, because it is meant to be a professional tool, and the way Zephyr is structured means that it does not want to compromise on its flexibility and adaptability. So there is this learning curve, and it is being accepted by whoever's working in the project and on the project. And it is also not really only meant like for the Arduino. This is about tinkering, this is for self-study, but Zephyr is about collaborative product development, and it has a full life cycle in mind. So there is a complexity that you just cannot get away with. And this complexity, that has implications, like the full transparency that you see in Zephyr with all the tools also means that till today we do not have a one-click installer. I know there are attempts, and Roberto mentioned that from AC6, that's a very good attempt, but still it does not work in every circumstance. I can tell you it doesn't work on ARM64 if you're running Apple Silicon, so we always have these exceptions. There's also no standard IDE, because again, the project has no interest, because everyone has different needs on the IDE, so it's all command line driven, and that also is a challenging one. And probably the hardest to get into is that because it's using dedicated domain-specific languages for different aspects like the variant management and the hardware abstraction, there's also no simplified programming model. You just have to write the real code. There is no setup loop simplification that we're used to from Arduino, or higher level functions like what you would find in Circuit or MicroPython. And then the last point on Zephyr is there is also a lot of meta stuff going on. These DSLs, they basically, by means of the build system, translate to source code. There's this heavy use on preprocessor macros that you need to get used to. So there are lots of layered complexities which really make it hard to get started somehow. Once you've seen all of this once, it starts to click, and then it gets easier the more you work with it, and maybe that's also reminiscent of the experience that the others were describing, in that once you have a basic body of knowledge, things start to make sense, and then the productivity picks up very quickly. But it's just this very first encounter with Zephyr that makes it so challenging. And this has been answered by the project, by the way, and there are great resources out there that the students can use, and probably also telling that your students, that we have offerings like Nordic, what's Nordic doing with their Deaf Academy. You've got lots of YouTube channels that have video tutorials. There are blogs written about it, but that's for self-study, and then you're on your own, particularly if you're a professional and not part of a student's course. So Stefan and I thought, how can we bring that back? How can we bring a group of people back into a room and offer classroom learning experience? Like face a problem and then have a group of people that you can talk to, and maybe some of these people even know the answer and help you out, so that you're not in this stop and go fashion all the time, where something works just until it stops working again, and then you're again figuring out yourself for hours to come what is the next mistake. So our challenge was, or how we phrased the challenge that we were attacking, is how can we have an environment where you can really build your first application. You've never ever touched Zephyr before, and then build an application within the first 5 minutes so that you just get hooked. That was our idea, because we see these professionals, they've heard about it, and they just want to get to know quickly, is that for me or is it not for me? And if they have to go through 4 hours of quick start guide, the answer is most likely that's not for me. I don't have time. So we really want to make it this. That's why speed is so important in this initial, at least to what we think in this initial phase. And we still want to teach the important Zephyr concepts. We want to put an emphasis on what makes Zephyr so different from other ways of embedded computing, like FreeRTOS or other commercial RTOSes. And then we want to build up enough motivation so that people go home. We don't tell them all the nitty-gritty details. We just want to send them home with enough motivation so that they, on their own, will try to solve the hurdles and the complexities involved. So that was the idea. And the talk is now structured in these three sections where we want to share with you what hardware we selected for the courses, because we also felt that we should do it on real hardware. It really has to blink. It has to, so you want to plug something together, you really want to have that experience. We then designed a couple of exercises, which I'll go through really quick. And then most importantly, and maybe that is of value to others as well, is the work environment that we set up, like technologies that also have been mentioned today, how we put that together to make it all work. By the way, that's the only AI-generated graphics I have in my slides, but I felt like I had to have one, so here you go, here you go. So, starting with the hardware. For the hardware, we put forth some selection criteria, and I have roughly split that in two now. First of all, what microcontroller to start with, like what SoC, so what would we expect that SoC to look like, and then what would we expect from the board that we were using in the classes. So for the SoC, for the microcontroller, we wanted to have something which is common, which is very typical in embedded computing today, and that really meant it should be like a Cortex-M or RISC-V controller, because that is just what you see 95% in the market, at least today. We also wanted to have something which got a ROM bootloader. The ROM bootloader has the interesting property that you can eliminate a programming tool altogether, because, and as you see that, the ROM bootloader will act as the programmer on target, and you can then just use the target like a flash drive and just drag and drop. So initially, you do not even need to bother with J-Link or any other stuff. And it also means that your hardware becomes unbrickable. You still can destroy it with a hammer, but you cannot destroy it you cannot flash it or erase the bootloader or something like that. So that's why ROM bootloaders were on our wish list. And obviously, because we wanted to teach Zephyr, it had to be well supported by Zephyr, which, by the way, for instance, rules out ESP32. Just a side note, ESP32 is a particularly bad choice when it comes to Zephyr, because lots of stuff just doesn't work, although no one's going to tell you. And then on the board level, we wanted to have a board that has just many onboard functionalities. Like there should already be lots of LEDs on it, lots of ways to interact with hardware without putting too much extra boards on top of it, which unfortunately rules out a lot of the vendor-provided development kits, because oftentimes they only have an Arduino Shield connector, but that's it, and maybe they have one button and one LED, but you cannot really do much without buying additional hardware. We still wanted to have a way that we could extend the hardware, like with standard connectors, be it Arduino, be it Groove, and we also wanted to have it at a sensible price, meaning it should be like sub $20, so that we could buy them for the courses ourselves without asking for too much budget from our companies. And we also wanted to make sure that if people wanted to keep using them on their private, they should be affordable. And they should also be orderable. Some of these dev kits are only being distributed through Mauser or DigiKey, which is for a private person not easy to get hardware from. So it should be on the typical maker stores like Berry Base or you name it, whatever you use for your maker needs. And that all brought us to this very neat board from a Malaysian company called Citron. It's their MakerPi RP2040. I think meanwhile they also have something for the 2350, but we really haven't felt the need to step up from the RP2040. And indeed, that really ticks a lot of the boxes that I just mentioned. It has got this ROM bootloader because Raspberry Pi has also been in education for a decade and more now, so they know what they need and what it means to work with students and pupils. It has plenty of RAM, it has plenty of flash. That also makes it great as a dual-purpose device because it also typically, when you buy it, it ships the CircuitPython. So you can also swap the image, and then you can do some easy exercises with pupils, say, like in a STEM course in a school. It has plenty of LEDs. It has buttons, RGB LEDs. It has even support for steppers and DC motors because it has a built-in H-bridge, so we can really start moving things, which the students love. We have servo pinouts. We have a buzzer and a speaker, so we can also play tunes. And we have these extensions, groove connectors, which is a very well-known extension system in the makerspace by Seed Studio, where you can again buy hundreds of breakout boards with sensors and actuators and what have you not. So this board is quite versatile in that sense, and at a price point, Stefan, correct me if I'm wrong, but at definitely below 20, maybe just even below 15. So it's really cheap. It's really cheap. We then put a few more stuff around it. We put that all in a neat box, and you can check later. We have one up there. You can take a closer look. We bought a couple of those groove breakout boards. We put down 4 micro servos to play with, a few buttons, some batteries. We provide this schematic, and the very first exercise in the session, in the meetup session, is to plug this stuff together so that it feels like real work, right? You have real hardware on the table and real cables to plug stuff together. And then the second part of the talk is about the exercises themselves. So we have the hardware, we have selected the hardware, now what to do with it. And the general structure of our materials follows this rough outline to the right of this slide. We typically start with a goal, and we keep every exercise self-contained and really particularly focused on one concept. Like if you look at students or software developers which might have had no exposure prior to embedded, we teach the very basics, like what's a digital I/O, what is an ADC, what's a PWM, I2C, and we just keep one exercise focused on one concept, and then we move on to the next. We provide some overview, we provide some background information. If you really want to understand what the different needs of use cases for PWM. And then we teach them in the exercise materials what hardware they would need for that particular exercise from the hardware selection that I just described. And then we walk them through using step-by-step instructions what they should do next, how the response from the system should look like. And sometimes we also deliberately provoke failures. So we do not tell the entire story in the exercise. So there are some points where things then will go wrong, and that we use as trigger points to discuss in the session the solution strategies. Because, I mean, we're also doing trainings for professionals a couple of days long. What we really feel important also in delivering these trainings is to teach the competence to work with these error messages, because you will always run into these error messages, and they are plenty. So it's much more vital, we believe, that we teach early on what you do with these error messages, and that you start to learn from what they are trying to tell you, even if the compiler screams at you hundreds of lines long because you forgot a closing parenthesis in a preprocessor defined. But just knowing that this is most likely to do with the preprocessor already helps. We need to take some time to test each step and verify that it actually works. And this is important because we typically need to redo that for every new version of Zephyr, because it's evolving, and we have to also evolve our materials. And we, last but not least, also provide solutions for the instructors, because we also want to open, or we have already opened up the materials to other instructors if they are interested in using the materials. So solutions for everything are also provided. The backbone of all of our exercises is actually the Zephyr shell. So in these meetups, we try to avoid coding for as long as possible, just using the built-in Zephyr shell and using the built-in command set that you can work with on the Zephyr shell to explore the hardware in an interactive way. And that already teaches you some of the features that make Zephyr distinct and unique, because in order to use the ADC shell, you need to know about kconfig, because you need to turn the ADC shell on. It's not automatically enabled for you, so you need to write some kconfig fragment. If you want to use a particular sensor, you need to at least write a little overlay to enable that sensor and then enable some more kconfig symbols on top of it. So that the irrelevant features are still demonstratable with using the Zephyr shell and without having someone write C code initially. So there's a lot of stuff to discover in Zephyr with the Zephyr shell alone. We also depict the different steps in the exercises by these icons, like when we ask them to work in the IDE, when they have to flash something by means of the bootloader, or when they should observe things going on, like the motor should move now, clockwise or counterclockwise, and so forth. And that helps us in the meetup sessions that people don't get lost in C coding too soon, because, and it was mentioned, writing C code is quite verbose because we lack a lot of abstractions, so you have to write a lot of C code, and you can probably make a lot of errors in writing that C code, and particularly with these preprocessor macros, the compiler isn't really helpful in telling you what you did wrong if you mistyped something. And then the materials themselves, we provide, or we started writing them up as docs as code. So we both serve a static website, which is freely available online, as well as PDFs. So we're using Sphinx, a documentation generation system, which is also being used by the Zephyr project, by the way, for the Zephyr documentation. So whoever has looked into the Zephyr documentation has already worked with Sphinx, at least with the output of Sphinx. And it's also meant for us to collaborate easily on GitHub, because all the materials, the content is actually being kept in a GitHub repository as well. And then if someone wants to improve on it, or if we want to add something, we just open a pull request on GitHub and have a normal review process going on from there. And that brings me to the third point, which is the classroom setup. And this is now really, again, this is, I think, very common to what we've seen earlier today already. We really wanted to have something which is just ready to go. If you only have in a meetup like 2.5 hours on an evening, you cannot even ask people to install a single thing. It just has to work. So it has to have no local install at all, ideally. And it should have everything pre-installed. All the tools you need, the Zephyr code repositories, and you alluded on that before, it is quite large if you do not specifically tune it a little bit. And the quick start guide isn't really great in telling you that, by the way, if you only run a Nordic board, you do not need to pull down all these 20 gigabytes of stuff. You only need one of those 40 HAL modules. It needs to be repeatable and resettable, because only we do a meetup once every couple of months. So we just want to pick it up again, and it should just work. For data protection also, we would prefer that we would not need to capture personal data from the participants, because then GDPR, so we don't like that. But still we need some accounts, because every student needs his own environment if you want to go that, as you see, into the cloud. So that was one of the considerations that we had. And last but not least, we also didn't want to incur any license cost on tools using. So this is not, well, you might debate whether this is educational purposes or not, but I'm sure that Saga would have an opinion on which license they would like to sell us, so that was also not an option for us. And really just to avoid any payment setups, like whose credit card is it then to pay the ABO or the service or whatever, the plan, and we would need to allocate budget, and that would just make things more complicated than needed. So we wanted to have some free and open source solution ideally. And this was that's brought us to what we now call browser-based embedded computing. The repeatable and the resettable, and we've seen that before, is today most likely easiest solved with container technology, like using a container image and then tying that, for instance, to a code editor like VS Code. There are extensions for VS Code like Dev Container, where all the tools run inside the container and just you're using the editor on your machine. And if you really want to have it ready to go, what you can do is you put the deployment, the container deployment into the cloud, like AWS or some self-hosted cloud, running on a Kubernetes cluster, say, and then all the students need would be a browser. So everything, all the tools, all we show them is a URL to a login, and then everything else for the session, for the course, happens within the browser. So this is what we ended up with using. For the data protection, there are two options out there. Because if you use that in a browser and you have each student running his own session on some cloud container, a cloud runtime, they have to have different accounts. So the way out for us was to provide fake user accounts. So they would just get a little sheet of paper with some fantasy name, and then we would just set them up in the browser, and afterwards we just get rid of all of these accounts. Again, because we did not want to store any personal identifiable information from the students. The tools themselves are all open source. I'll show you the options on the next slide, but it's not completely free, obviously. If you go into the cloud, you have to pay the cloud costs. So whatever EC2 instances you need. The good news is they do not need to run 24/7. We spin them up before the meetup takes place. Then they run a couple of hours, and then we wind them down afterwards. So it's more like 10 euros than it is 100 or something like that. So it's still manageable. For the deployment options, we've played around with a couple of options, and they have all their ups and downs. So we can really choose depending on the current scenario where we'd like to do that. So probably nowadays, the simplest to work with is GitHub Codespaces. That's like these cloud-based IDEs as a service right from your GitHub repository. You can, if you are a registered user on GitHub, and again, they have to be registered, but we still do not need to know them or their account name. They just click a button, and then they have their setup immediately up and running in GitHub. The downside is that these GitHub containers have a size limitation because they need to be pulled to a virtual machine, and if that takes too long, if they time out, then the GitHub Codespace will never appear. We ran into that issue with the Zephyr CI image because that's a couple of gigabyte large. So the GitHub, the project containers don't work with GitHub Codespaces. We're also using self-hosted cloud IDEs. That's the least amount of work for students because they just get a fake account and then off they go. There are a couple of options out there. The most notable ones that we've played with are Coda, which is free to use, but not really open source, and some size limitations apply. Or the full open source would come from the Eclipse project by the name Thea, which is kind of the successor of the Eclipse IDE for desktop PCs. Problem with this one is you need to have a Kubernetes cluster somewhere, and you need to have at least one person in the team who is willing to write all these Kubernetes YAML files and wire and plug the stuff together. So there is a lot of maintenance on your side, which is also sometimes not feasible. And then last but not least, we also see people with a Linux machine coming to the meetups. We can also offer them local dev containers. So it's still all in a container, but obviously you can run that on a Linux or Windows PC easily and tie that to VS Code. And that's what that looks like. Obviously, there are a couple of caveats and some things that do not work. But first and foremost, you need a browser on your PC. All the tools are running elsewhere on a cloud computing instance. And you download from the browser window the final binary. And then, because we're using this ROM bootloader, you pull that to the local file system. And then from there, you pull it over to your target. And that's all you need to do. And that works exceptionally well on most platforms. The notable exceptions are some MacBooks. We've seen some people showing up with MacBooks where for whatever reasons that the target wouldn't show up, but that's really like 1 in 100. So the majority of setups just works like that. And by the way, if you want to play, there are a couple of more links. That's all on GitHub. You can easily check that out yourself. So just a quick recap of what we've been doing with that setup so far, where the experiences are coming from with this setup. That's the materials themselves. I just put that on one slide, so everything's on GitHub. We are not using Zephyr as such. We are also working on another open source project called Bridle, which is our blueprint, our downstream blueprint that we're also using with our commercial clients to show them what their software development repository structure should look like. And then on this Bridle project, we then put the tutorials repository and what we call the dojo, the Bridle dojo, to make use of that. So the minimal dev container that I was mentioning that also would work in GitHub Codespaces, that's the dojo. The training materials themselves are this tutorials repository, and we also from the main of this repository deploy the materials to a website. Right now the materials are all in German because that started out as a German meetup idea. But we also have had students that were just running this through Google Translate with sufficient results. So it's not great, but it works. And we are looking right now into translating everything to English, but for the time being, the materials are German only and they are permissively licensed, and we welcome widespread use and contributions, obviously. We've done like 8 meetups starting in December 2023. So this is now, we're at the end of year 2. 8 meetups. Meetups typically happen after work. So we start around 6 p.m. So people have had already a long day at work. So again, it needs to be fun. It needs to be engaging and not too burdensome. And then we also have had the opportunity with Lenka together to try that out in 2 courses at universities, once in Liberec, once in Prague last year, so that in total we have now been working with 120 students-ish on the materials. Typically, we got 12 students in a session. We had once 20. That was a bit of that was challenging because it was just 2 of us, and then there are problems, and we need to go around, but a group of 12, I know this probably ideal given your class sizes, but that's the pleasure of working with industrial and professionals, that the classes get smaller. Yeah, that's what it looks like. Depends on the scenario, but always hardware on the table. People are working through the exercises. We help them. Sometimes we get some support from other friends helping us wherever we are. And so far, it's always been great fun, and we've also got good feedback from the participants. Lessons learned. We really were convinced by the fact that we are working with real hardware that really is making a difference, we think. People like tinkering around with stuff. The hardware we choose was surprisingly robust. Like this Cytron, we never had one board breaking so far through 10 sessions, so it's actually still working. I was expecting more churn initially, like that we would need to replace parts a lot sooner, but that hasn't happened yet. We really think that this browser-based IDE was crucial for the quick start because it really eliminates any local setup whatsoever. There are caveats though. You cannot debug, obviously, because we never use a programmer, and it's also not doable with the browser-based system. I've been talking to the Eclipse Thea guys whether they would consider doing it, because I knew that the Embed OS browser-based stuff once was able to do that. And I've also been talking to Kyle about it, and it might come at some point, but it's unclear when. So there were some licensing issues around it. So right now, debugging from the browser, although technically feasible, is not available in any open source project as of today. I mentioned that most laptops really work in that setup, but not all. And then if you can, we also learned that if you have different options available at the same time, that also increases your availability. We had once a meetup in southern Germany where actually the idea was that they have their own Kubernetes cluster, But that had some hiccups, so we had to switch, and then we were happy that we could switch to GitHub code spaces, so at least we could move the workload a little bit. So still be prepared for things, surprises in deployment. And I think with that said, yeah, we have a few ideas of what comes next. In particular, we want to combine the motors into something more interesting, like a robot arm, to increase the integration level of what we're doing in the classes. And right now we're also thinking about team exercises where we'd like to do some division of labor in the session and say, you guys work on the UI and you guys work on the sensing or on the whatever, and then we bring that all together, because that is another strength of Zephyr, that you have these clear-cut interfaces, which then make sure that things become easily integrable. And I think now I'm at the end. Thank you.
Thank you, Tobias. Any questions? So could you please have
Thank you. When you, in the slides where you were talking about the Zephyr shell, you also mentioned West.
Yes.
Which, I'm confused about this. Are you building Zephyr in the board?
No. We're using West, so we show them West. But in order to get the Zephyr shell into the board, you need to build an example with West. So actually, it's two terminals, if you will, one on the PC and then one on the target.
Okay. So
yeah, okay, yeah, that's fine.
So this is what confused me.
Okay,
so
sorry that. Yeah, sorry for that.
Okay.
Yeah.
Thank you.
It was this one, right? Yeah. Yeah. So this is the Zephyr shell that would come back from the target. And by the way, you can use, there is web serial. There are nice readily available websites for the browser where all you need is web USB, and then you have also the terminal emulator within the browser. So you really do not need any local tools installed.
any more questions? So I also tried some examples from the Bridal project, and it gave me some great insights. It was a little bit tricky because I already had tried Zephyr on the same hardware, on the same machine, and it intercepts to each other. So there was some nice debugging sessions about this. But it's a really good startup example there. Okay, anything from your side? If this is not the